Welcome to our last exercise in Chapter 6 that we're actually doing. This one is dealing with doing some similar triangles proofs. Now, in your notes, we've got 4 tests for similarity. But what I don't say in the notes, and I just want you to be aware of it, is that we're actually using the old approach. With the New South Wales syllabus that has just come in the last little while, so you're in year 10, so it's your second year, you're the second year of the New South Wales syllabus, we don't actually use the similar triangle method of saying SSS, SAS, AAA, RHS as I've listed now, as I've just pulled it up. So this is a table that's in your notes. It used to be a case of you could say something that by SSS, two shapes are similar, or by SAS they are similar, or by AA they are similar. We don't actually use these abbreviations anymore. They're still useful to know because they give you an idea of how you can check for similarity, but when you actually do a proof, you're supposed to actually make the statement rather than the abbreviation to show that you've proven two things are similar. So when you're dealing with similar versus congruent shapes, you'll notice that similar shapes have SSS, as well as congruent shapes had SSS. You'll notice that congruent shapes and similar shapes had SAS. Congruent shapes and similar shapes use RHS. The only difference is congruent shapes used AAS to prove that two triangles were congruent, where similar triangles don't use AAS, they use AAA. So the tests are almost identical except for that one difference. Let's try looking at our first example now. Now the question says, find a pair of similar triangles amongst those shown and give a reason for your answer. Well, I've got triangles A, B and C. I haven't got a clue initially which one I'm interested in. So I could be comparing triangle A to triangle B, or triangle A to triangle C, or triangle B to triangle C. I don't know. So I'm just going to start by comparing A to B. Now, here's my little table, remember? So I can use any one of these 4 approaches to prove things are similar. Let's have a look. If I'm comparing triangles A and B, they both have a 135-degree angle. So an angle could work. I don't have any other angles, so I can't use triple S for 3 sides. I can't use 3 angles. I can't use right. It has to be side angle side. Now remember, side angle side when I'm doing similar triangle questions means 2 pairs of corresponding or matching sides are proportional. They're in the same ratio and the included angles are the same. So let's actually have a look at my triangles for A and B is what I'm starting with. If this doesn't work, I'll have to match A and C or B and C. Let's see. Now, on triangles A and B, I'm going to look at the sides. So what I'm actually doing is I'm going to take the larger of the given sides, and you'll notice that from 135 degrees I've got a larger 3, that's larger than the 2 centimetre side, and on this one I've got 135, so I've got 2 sides, 4 and 6. I'm going for the larger of the 2 sides. Now I could have done 3 divided by 6. I'm doing B over A, the bigger one over the smaller one. 6 over 3, this side length over this side length, they divide to give an answer of 2. That's where I'm just going to stop for the moment. Now I'm going to compare another set of sides. Well, the other set of sides I'm going to compare are the shorter ones. So the bigger triangle over the smaller triangle would be 4 over 2 for the side lengths. That cancels down to 2 as well. Well, because they both cancelled to 2, that means these shapes are in the same proportion. This triangle B is twice the size of triangle A. It's got a scale factor of 2. If I have a common angle between those sides, which I do, matching angle or a corresponding angle of 135 degrees, that means that triangle A and triangle B are similar. Why are they similar? Well, I used two sides and an included angle. So I'd say because two pairs of sides are in the same ratio, they're in the ratio of 2 to 1, they've got a scale factor of 2, and the included angles equal, the triangles are similar. So that was lucky that A and B were the ones that matched up. If I tried matching up A and C or B and C, the ratio, the scale factor wouldn't be the same for both of them when I divided them. So luckily, picked the correct pair of triangles to match up first up. Now, example 2 says prove that triangle ABC, so there's A to B to C, triangle ABC is similar to triangle CDE. I'm going to prove that this triangle and this triangle are similar, and all I'm given is one pair of parallel lines. Okay, well, because the lines are parallel, I've got a Z shape happening. Those two angles there are alternate. So angle BAC and angle CED are both equal to each other. Why? They're alternate because AB and DE are parallel. Parallel lines mean that those angles are alternate. What else do we know? Well, we've got some other angles. Let's try looking at the shaded green ones. Angle ABC, this one here, that's A to B to C. And angle CDE, C to D to E. They're both alternate as well because I've got parallel lines and there's a Z shape. Backwards sort of sideways one, but it's there. So they're also alternate because AB and DE are parallel. Well, I've only got one pair of angles left. Why are they equal? Well, they're equal because they're vertically opposite to each other. So I've shown that I've got 3 matching sets of angles or corresponding sets of angles. So I can say triangle ABC is similar to triangle CDE since they have 3 pairs of matching angles. And a fancy way to say that is that they are equiangular, but you don't have to remember that. You could just say since they have 3 pairs of matching angles. You shouldn't write by AAA because that's using the old terminology which is no longer part of our syllabus, as I mentioned earlier. Okay, example number 3. It's broken into 2 parts. Now, looking at these shapes, I'm not actually interested in showing that these are similar triangles, but those 2 angles would match up because I've got 2 curved and 2 double curved, so they match up. They're similar shapes. I should have said in the question, find the value of the promunal in each where the shapes are similar. Now, when the shapes are similar, that means that the proportion matches up. So I could compare the small triangle to the big triangle, or I could compare the big triangle to the small triangle. The side length I'm looking for is A. So what I'm going to do is look at A, and it matches up with the 18 length. So I'm going to write A over 18. So I've got the small triangle on the top, the large triangle on the bottom when I look at the fraction I've created. Then I'm going to look at some other sides. Well, I know on the small triangle I've got a side length of 8 that matches up with a side length of 14. So they'll divide and give the same ratio as A divided by 18. Well, there you go, I've got it. Now you could cross multiply or you could do whatever you like with this one. I'm going to times both sides by 18, and when I times both sides by 18, I get 8 times 18 over 14, which cancels to 10 and 2/7 if I take it to a mixed fraction. So A is 10 and 2/7 centimetres long. So it's a bit messy, but can be done. Let's try part B. Now, with part B, it's important that you can recognise that we've got 2 triangles that are similar. Because I've got parallel lines, there's my parallel lines, there's an F shape there, which means that those 2 angles are equal. It also means these angles are equal because I've got another F shape going backwards in that way, and I've got a common angle. So the triangles are similar. I've got a big triangle, and I've got a little triangle, and they're similar. So it's important that I recognize that. The question again should have probably said, find the value of the pronumeral on each of the following where the triangles are similar, because I'm not wanting to do a test for similarity here. I'm wanting to find a side length. Now, I'm actually going to redraw both of the triangles. So you can see I've got the small triangle and the big triangle. There's my small triangle, 9 and 15. The big triangle has 16, and that's C, and that's 15, so C plus 15 is the length across the bottom. Now I've got my length across the bottom. It's a case of matching up sides. So if I looked at my big triangle, has the length I'm looking for, it's C, but it's also got a plus 15 next to it, so C plus 15, if I divide it by, it matches up with that side, so I divide it by 15, that will give an answer that is the same ratio or proportion as doing 16 divided by 9. Now I've got myself two fractions equal to each other. I could cross multiply, and if I do that, I'll get an answer, but I'm going to choose just to times both sides by 15 initially. If I do that, the 15's cancel on the left hand side. I get C plus 15 is equal to 16 times 15 over 9. 16 times 15 over 9 can be figured out on the calculator, and it is going to be 26 2/3 if I write it as a mixed fraction. Now I'll just minus 15 to both sides. 26 2/3 take away 15 gives 11 2/3. So C is 11 2/3. Again, a messy one. Normally they'll be probably whole numbers in the textbook because they're a little easier, but that's to show you that the process works. So there are your examples. It's now time to try exercise 6E. So you have a test coming up soon on exercises 6A through to 6E. Have fun doing this final exercise.